Alright gang, here we go. This is for Chem 2 Unit 13, talking about reduction potentials and being able to calculate cell potential. Alright, C-E-L-L, not your ability to sell if you're anyway, so you got reduction potentials. So last video we talked about electromotive force and the idea that voltaic cells have a certain amount of potential energy, and we want to be able to use this potential energy to create voltage, right, and be able to measure it and be able to hopefully put it to work to like run batteries or cell phones or so on and so forth. Okay, and so the first step along this way is to be able to identify, well, how much energy is going to be transferred, and we call this Ecell, and it's measured in volts. All right, so in order to do this, we use a table of standard reduction potentials, and these standard reduction potentials have been tabulated over dozens of years by dedicated chemists. Okay, and so we can use these values, all right, and they're compared to the reduction of hydrogen as the standard. All right, and so always keep that in mind, that the standard hydrogen electrode is what we're comparing it to. The standard conditions for these guys are always at a 1 molar, 1 atmosphere, and 25 degrees. So if you're at something other than that, you kind of you'd have to find different tabulated values or do something fancy along your way. So make sure you're always at standard conditions. We'll always be at standard conditions, so you don't have to worry about it too much. All right, here's a bunch of reduction potentials. All right, they have them nicely listed from high to low as we go. So this is the reduction potential for all of these reactions. Notice that they're always reduction potentials. We're going from we're adding electrons. Reduction is gaining, right? Oil rig. Okay, and so we're gaining electrons in all these, and they show all these half reactions. Okay, and so we've got fluorine and permanganate, chlorine, dichromate, etc., etc. Right, and we get some more over here. Here's the hydrogen electrode. Notice that this guy here is what we're comparing it to that I just mentioned, and it's defined as 0, and so we're comparing it to the rest of those. All right. And then here's some more here, and so sodium and lithium really have very, very low reduction potentials. All right, so the standard hydrogen electrode is the reference. This is what we've defined as 0. All right, and you might see it abbreviated as SHE for standard hydrogen electrode. All right, and so the way this kind of occurs is that you've got a platinum electrode right here with some sort of hydrogen source, usually an acid, and where we get when reduction occurs, at this spot here we get hydrogen bubbling against this guy here, and we get this reaction where hydrogen gas applies up here. So where you have that if we put zinc in acid, it starts to bubble and form hydrogen gas. This is exactly what's happening. All right, we get this these hydrogen gas formation, which is just a redox reaction. All right, so anyway, so we get platinum, H plus reacts here, forms hydrogen gas. If it goes backwards and it's oxidized, then the hydrogen builds up on the platinum and then breaks off to form this acid and water. All right, and it's formed as 0. All right, now remember, reduction potentials are always at 0 value, and so if we flip it around, if something's being oxidized, we have to take the negative of our oxidation value, or a negative of our reduction, to get the oxidation potential. All right, so how can we use these reduction potentials to calculate the standard cell potential? Well, we just use this really simple formula. You take the reduction potential that happens at the cathode minus the reduction potential that happens at the anode. So cathode minus anode. So essentially, it boils down to is you need to figure out which one's being reduced and which one's being oxidized. Remember, red cat, unox red cat, so this is where reduction happens. So if we can figure out what's being reduced and figure out that electrical potential, and then we subtract the anode, and so this would be what's being oxidized. All right. Okay. Notice that it's also an intensive property. Okay. So it doesn't matter how much you have because it's per unit of charge. So for example, if you have an anode in some cell where the reduction potential is negative 0.76 and the cathode is positive 0.37, all we have to do is just plug these guys in. Anode minus cathode, 0.34. Why did they change that? It was 0.37 right here. That seems silly. But anyway, so 0.37 minus a positive 0.76, so this would become 0.11, right? It's hard to do math on a video, okay? Don't judge me. 0.34 plus. No, not 0.37 plus 0.76. All right, 1.13. Oh my gosh, that was embarrassing because they're getting added, not subtracted. Anyway, so 1.13 would be the electrical potential of this cell. Okay. So here's a reaction, okay, that was just going on. We've got copper and zinc, all right, and so we get 1.1 volts traveling through it, which is exactly what we just, or pretty dang close to what we just calculated for our reduction potential. Okay, and it's exactly what they calculated because they used the right value here, so they got the 1.10 volts. Anyway, so you got your anode, and the zinc is being oxidized, and then at the cathode, your copper is being reduced. Okay. Says calculating. So for the zinc copper voltaic cell shown in 20.5, we have this overall reaction, and the Ecell equals 1.10. Given that the standard reduction potential of zinc is 0.76, calculate the reduction potential for the reduction of copper, 2 plus to copper. All right, and so all we have to do here is work a little backwards. So that's exactly what they're going to do here. So let's walk through. So where they solve it, skip, but you can read that plan if you want to, but it's easy enough. We know that the E cell is equal to the reduction at the cathode minus the reduction at the anode. All right, so our E cell is 1.10. The E cell at the cathode is what we're solving for, and then the anode is negative 0.76, and we know that because number one, they said it, and then number two, we can also look at our little graph. Zinc 2 plus is that 0.76. We can plug that in, take 1.10 minus 0.76, and we get 0.34 volts. So, but we could have looked that up anyway, so why is that helpful, right? It's right there. For this next example, we're going to do the same idea, but we're going to have this indium, okay? So we don't know, the indium is not on this chart. Oh yeah, I plugged it in right here. Indium isn't on here. All right, so we can take we can use this in order to find indium. Okay, so we know that the standard cell potential is 1.46, and we want to be able to find what the reduction of indium IN3 plus to IN plus is, right? So we know it'd be 1.46 is equal to the E cell at the cathode minus the E cell at the anode. Okay, so we find bromine on our list. It's right here. All right, there's our Br2. Oh, shoot. Ooh, they tried to trip us up here, didn't they? They tried to trip us up. Look at this real quick. Okay, so we know that the overall equation here, okay, is the cathode minus the anode, right? So it's a E cell is equal to the cathode, and I'm not going to minus the anode. And so look, we have to identify, well, which one's the cathode, which one's the anode. Remember, unox, red cat, so we can figure out which one's being oxidized. So oxidation is losing, so this guy's losing, so this guy's going to be oxidized, so that means he's the anode. Ooh, so he's a little different. And then the bromine is gaining, so that means he's being reduced. So that means this is the cathode. All right, and so so now this is a little different than the one we just solved for, because now we're going to be solving for the anode portion. Ooh, they almost got us. All right, so yeah, not such a big deal, but a little fun. So if we solve for the anode is going to be equal to, well, we can subtract that over, so the cathode minus the E cell. All right, and so that means the E cell, or the E reduction at the cathode, is equal to, or sorry, the anode. Oh my goodness. The anode is equal to the cathode, so that's our bromine value, that's the 1.06, minus the E cell overall, which is the 1.46, right? So the E cell, E reduction at the anode is going to be equal to negative 0.40 volts. All right. We could double check our work by plugging these guys in, right? And we'd get 1.06 minus a negative 0.4, and you'd get your 1.46 volts. All right. This one's a little different, right? So now we're going to calculate E cell from the reduction potential of this guy here. All right. So what we have to do is figure out what our two half reactions are. So, and this is the same one we looked at the previous video, so that's handy. So we got Cr2O72 minus, and it's going to Cr3 plus. So that's one half reaction. And the other half reaction is I minus going to 2. All right, and we got to figure out which one's being reduced, which one's being oxidized. So we could look at the chromium, but that would be a pain because we'd have to look at oxygen and hydrogen and all that stuff. Nobody wants to do that. So we'll just skip that for now and do the iodine, right? So the iodine, we need 2 of these, right? Because you got to balance the i's, and then we don't have any oxygens or hydrogens, so we don't have to balance those. So now we got just the electrons. So we got 2 negative over here, 0 over here, so we're going to add 2 electrons to the right-hand side. So you got 2 electrons, negative 2 over here, and balanced, right? So we're losing electrons, so that means this guy's oxidized, so that means this is the anode, okay? And then the dichromate would have to be reduced. And if we really wanted to double check, we totally could. This would be the cathode, right? Cathode, an ox-red cat. So the Ecell is going to be equal to the cathode minus the anode. So we need the value at the cathode. So that's our chromium dichromate. This guy here, 1.33. All right, minus the iodine. So we got to look for iodine. Oh, it's right there, 0.54. So you take 1.33 minus 0.54. You get 0.79. All right, and that's it. So pretty easy stuff. Oh, and then they work through it. Let's see if we get the same answer. 0.79 volts. Nailed it. All right, and that's it for this video. Anyway, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.